So, hi guys, this is Dr. Edwards again. I want to give a little bit more information on the quantum harmonic oscillator. I'm going to take this information from the main textbook of the course, David Griffith's book. So, what is going on with the harmonic oscillator? It turns out that, as I indicated previously, we need to get the expression for the potential energy. And here we're going to start with the classical expression for the force of a spring acting on a body of mass m. So taken from Newton's second law of motion, here you would get a solution of this form for this equation, which is the equation, the classical equation for the position as a function of time for this harmonic oscillator. Now, what is the resultant expression then for the quantum oscillator? The angular frequency is the square root of k over m, where k, I say again, is the force constant and m is the mass. Excuse my voice. It turns out then that the potential energy corresponding to this force is 1/2 kx squared. So if we go with that expression, we find that the quantum potential in its simplest form is 1/2 m omega squared times x. Okay, so let me get on. So now if you plug this expression for the potential energy into the Schrodinger equation, which is done here, this is the independent time-independent version of the Schrodinger equation. Now solving this equation is to get psi as a function of x. Okay, this equation then, and I'm going to skip through the laddering method and go on to the algebraic method or the analytical method. So the equation that we just saw is this one. Now we're going to change variables from x to c. And so when we make this substitution, that c is equal to the square root of m omega h bar times x. X is not under the square root bracket. And make the appropriate substitution, you get this equation here. D second psi, dc second is equal to c squared k times psi. And we want to get psi. It turns out that this is not a trivial equation to solve, but it's already have been solved in the annals of mathematics, and it's called by many the Hermite equation in French, or the Hermite equation in English. I will call it the Hermite equation. Now, solving this equation, it turns out that you need to handle it in two different steps. One is to look at the solution when c is much greater than k, and that's for when x is very large. Then the differential equation simplifies to this expression, and you can show then that the solution goes as some constant capital A, e to the negative c squared over 2 plus b, e to the positive c squared over 2. The physicists want a well-behaved solution that does not blow up at infinity. Therefore, we're going to assign capital B 0. So that takes this term out, leaving just this term as a legitimate part of the solution. Okay, let's go on. So now if you substitute this back into the differential equation, what you wind up with now is equation, let's see, you write it this way, as psi of c being equal to h of c e to the negative c squared over 2. You substitute this equation back into the Schrodinger equation, and now you get this equation here to be solved for h as a function of c. The best way to solve this equation is to use what's called the Frobenius, series method. And that's what's going to be used here. Here's the spelling of this word. And so you get each term, and now the secret then is to find these coefficients h sub j. You go on with the process, and you get this equation here. You get this recursive relationship that aj plus 2 is related to aj. Therefore, if j is 0, then a2 is related to a0. If j is 3, if j is 1, well then a3 is related to a1. So we get then the recursive relationships that all the even coefficients are related to a0 and all the odd coefficients are related to a sub 1. Therefore, go on and write then h of c as even terms and odd terms. We still haven't solved the final answer because what we want is a normalizable solution. Whereas what you have here, the solution is not necessarily normalizable. What causes it to be normalizable is when aj plus 2 term is approximately equal to 2 over j aj term. And if that is the case, you get then that h of c is related to this expression here. This term here has come out of finite difference method that's not spoken of right here, but this is an important part of the process and leads to this expression here, that finally h of c is equal to this term here if it does not terminate. And that's the term that you don't want it to have. The only way to keep it from not being of this term is that the expansion has to terminate. Which expansion that I'm speaking of? This one right here. So it turns out that the numerator here has to go to 0 for some j to keep from h being in this form, which we do not want it to have, where it goes to infinity when c goes to infinity. Therefore, the important result then we get is that k then becomes these discrete values. And when k becomes discrete, the energy then of the harmonic oscillator becomes discrete for any value of n. N equals 0, 1, 2, 3, on and on and on and on. Now let me go on then and say a little bit more about the solutions that you finally get. He speaks of the 0th one here. Let me go on and indicate the final value. This now is the final value of the wave function that's normalized for the harmonic oscillator. It looks a little bit forbidding, looks fairly difficult, but it's not so bad. It is the product of two terms. There is that e to the negative c squared over 2. These are the Hermite polynomials, as I say. So we have to have the polynomials to keep that small h, as we talked about earlier, from going to infinity. And this expression here normalizes the wave function. So when you integrate psi against its complement psi star, the integral of that over all space should be equal to 1. And now the author shows a few of the Hermite polynomials for the ground state, h sub 0, for h1, etc., etc. So that now brings me to showing the results. I do not claim to have solved totally how you arrive at this expression. It is important, though, for you to know that this equation satisfies completely the Schrodinger equation. So that's the answer to this equation, going back to it. So you'll see it one more time. That is the general equation that we start with right here that we have to solve. This is the equation. When you solve it, you get these discrete answers for psi, because the energy for the harmonic oscillator, the energies are discrete as well. Now, one of the things I'm going to have you to do is to show that if I have any one of these, particularly psi sub 0, I will have you to show that the integral of psi star 0 times psi 0 should be equal to 1. And psi star 1 times psi 1 dx should also be equal to 1. So that's a special problem that I'm going to give to you as we go through this treatment. Okay, that's what I wanted to give you so far. These are some representation of the wave function and the wave function squared for the various cases. This is the ground state. This is the first excited state, on and on and on and on, okay? So this is one more illustration of stationary states. We did the expression for the infinite square wave, and we get an exact solution. And now for the single particle harmonic oscillator in one dimension, we also get an exact solution. And I want you to have these two. These are standard for this level of quantum mechanics, okay? All right, guys, have a good day. And I will be giving additional homework problems for you to do on this subject. Have a good day.